Right. So I want us to start with this question. As I said, I took it from the IB. I found it to be quite an interesting question because it covers quite a vast, array of things. Right. Now they say to us, we've got oxygen and nitrogen present in air, and in internal at 1,200 degrees, right? Now, they give us this reaction. Remember, ladies and gents, the moment that we are told delta H is greater than 0, I always, kind of use this Pac-Man symbol. Ne? Right. If you think of Pac-Man in this case, that being the Mouthka Pac-Man, Pac-Man is actually facing towards the left. So what this means, this is an endothermic reaction. Okay, so delta H greater than 0 means it's endothermic reaction. Please, if you haven't watched our series on chemical equilibrium, after this, you have a date with YouTube. Okay. Right. And
Yes.
and what I'm going to try and do is obviously explain in such a way that it will also assist you. Right. So if you think about it, so what this means when we say a reaction is endothermic, what it means is that this reaction requires energy in order to react. It means that nitrogen and oxygen, sorry, will not react on its own without you putting in an external source of energy, heat in this case, right? So in order for nitrogen and oxygen to react, we need to put in heat, and as a result, we'll get nitrogen monoxide. Okay. Now, what this also means is that if the forward reaction is endothermic, then it means that the reverse reaction is exothermic, meaning that nitrogen monoxide can also decompose. Remember, this is a reversible reaction, right? So it means that nitrogen monoxide can decompose to form oxygen and nitrogen. But remember, when it forms oxygen and nitrogen, it means it's able to also produce energy. Okay. Now, I want you to think of, I'm trying to think of an exothermic reaction. If you think about boiling water, right? To heat up water is an endothermic reaction. Why? Water cannot just heat up on its own, right? Without you putting, electrical energy on in the form of, your kettle, right? So that would be an example of an endothermic reaction. But think about water cooling down, right? Water cooling down, that happens on its own, isn't it? So it means if you're changing from water to, let me say, vapor, all right? Vapor is steam, isn't it? So from water being a liquid to vapor, what you need to do is you need to put in heat as external source of energy in that case. So that's an example of an endothermic reaction. But to change from vapor to water to liquid, in this case, that reaction occurs on its own. You don't need to put energy there. But then what it means is that when it changes from vapor to liquid, it actually also emits energy in the form of heat. Of course, we are not able to see that, okay? But it means that we are also, in that case, heat is actually given off. I hope that makes sense. Ne? So this reaction we know is an endothermic reaction. There are some things that I'm going to say as I continue. Right, now, they say, what is the magnitude of the equilibrium constant? Oh, sorry, I skipped a part. They say the equilibrium constant for this reaction is 1,200, at 1,200 is 1.1 times 10 to the minus 5. Now, in this case, what does this mean? It means this is a very small value. If you think about it, this value is about 0.000011. Okay, so what does this mean? It's a very small value. So if we've got a small equilibrium constant like this, where the equilibrium constant is less than 1, what it simply tells us is that we've got a very poor yield of the products. Okay, so it means that we are forming less products than there are reactants. Okay, please tell me that makes sense, ladies and gents. Are we good?
Can you please repeat, sir?
Okay, right. I'll say this again. So when the value of the equilibrium constant, can you see this is a very small value, né? What it simply means is that there is a poor yield of products. It means that there are less products that are being formed, products being what is on the right-hand side, okay, than there are reactants. So it means you have maningi reactants and you have low amounts of products, okay? So remember, when the equilibrium constant is less than 0, so it means that you've got less products, simply put. Okay. Are we good?
Yes, sir. Thank you.
All right. You're welcome. All right. So now they say to us, fully explain the effect of high temperature on the yield of nitrogen monoxide. Okay. Let's get to the part where we explain about the fact that it's endothermic, right? Now, please, I want you to listen to me very carefully, right? So, when we say this is an endothermic reaction, right, then it means that every time, or rather, let me say this is a blanket statement. Né? Whenever we increase temperature, it always favors, in this case, the endothermic reaction. Please remember that, né? That an increase in temperature will favor the endothermic reaction. Now, in this particular case, which reaction is endothermic? Is it the forward reaction or the reverse reaction? We did say it is the forward reaction. You remember that, né? They said delta H is greater than 0. So it means that the forward reaction is endothermic. Okay. But what that means is that the reverse reaction is therefore exothermic. Okay. Right. So we know that when we increase the temperature, we will always favor the endothermic reaction, right? But which reaction is endothermic? It's the forward reaction. Okay. So, so in this case, when we increase temperature, or high temperatures in this case, will actually favor the forward reaction, and therefore it will increase the yield of nitrogen monoxide. So when we favor the forward reaction, it means we are using up the reactants to form products. So as a result, it means that the yield of nitrogen monoxide will be improved. Okay. An increase in temperature, sorry, I was supposed to say temperature there at the top. So an increase in temperature, will favor the forward reaction. Will favor the endothermic reaction. Favors the endothermic reaction. Okay. But what do we note in this reaction? The forward reaction is endothermic. Forward reaction is endothermic. So what does that mean? It means that the forward reaction will be favored. Okay. So the reaction is favored. And so what does that mean? It means that the yield will increase. Okay. So that is how we'll explain it. So an increase in temperature favors the endothermic reaction, but we noted that the forward reaction is endothermic, so therefore the forward reaction will be favored, right? And in this case, it means that our yield should increase. Happy days. Now, they say to us, we've got internal combustion engines also produce very high pressures, right? They say, what is the effect of high pressure on the amount of nitrogen monoxide formed? State only increase, decrease, or remain the same? Well, obviously, I will have to explain in my case because I want you guys to understand. Now, remember, when we are looking at pressure, now please, I want you to listen carefully. Né? So, when we are looking at pressure, right? Before you can answer anything that has to do with pressure, you must always look at the number of gas moles on the left or and on the right hand side. Now, how many gas moles do we have on the left hand side? Well, this guy is a gas, so it's 1 mole of gas. We've got another gas. How many moles? 1 mole of gas. So, which means we have 2 moles of gas on the left hand side. Okay. But how many moles of gas do you have on the right hand side? Well, there's 2 in this case. Right. Now, I want you to note an increase in pressure will always favor the side with lesser gas moles. Okay. So, so if you've got less gas moles on the right hand side, we will favor the right hand side. Okay. When we increase pressure. But this time, what do you notice about that? Those gas moles? We've got an equal number on the left and on the right. So an increase in pressure will not affect any of the reactions, right? So as a result, it means that they said, what is the effect of the high pressure on nitrogen monoxide? It will remain the same. It will not be affected. Why? Because the number of gas moles would be the same. Let me just make a hypothetical reaction, or rather a situation. Let's just say, for argument's sake, we had just an example. Let's take 2SO2, okay, plus oxygen, giving us 2SO3, okay, and all of those are gases, right? It's a reversible reaction. Sorry about writing it so clumsily. Right, so if you look at this, you have 3 moles of gas on the left, you've got 2 moles of gas on the right. So if they asked us the same question for a reaction like this, then you'd say, well, look, when you increase pressure, you will favor the side with the less moles of gas. So where do we have less moles? It's on the right-hand side. So in this case, when you increase pressure, you would favor the right-hand side. Why? Because there are less moles of gas. Okay? When you increase pressure, that is. Okay, so it means that SO3 would actually increase because you are favoring the forward reaction. Okay, so in that case, that is how we would apply it. But in this case, because we've got 2 and 2 on the left and on the right, so as a result, that is why our answer would be it would remain the same. Okay, right. Now, they say to us, if oxygen rich air, all right, that is air with a higher concentration of oxygen, entered the combustion chamber, how would this affect the amount of nitrogen monoxide formed? State only increase or decrease or remain the same. Okay, so in that case, what are they trying to say to us? If we increased the amount of oxygen, right? What would happen to the amount of nitrogen monoxide? So anytime that we increase the reactants, right, we will favor the forward reaction. Okay, so an increase in the reactants will favor the forward reaction. Why? Because we now have to use up those reactants that have been introduced. Okay, so as a result, when we favor the forward reaction, it means that we are going to now form more nitrogen monoxide. I do state again, please make it a point, sorry, that you watch that YouTube video that I did on chemical reaction. Okay, please make it a point that you have a look at that so that you can understand the section a bit better. Right. Now, they said state increase, decrease. So definitely it should increase. Okay. Right. Now, we're going to get to the part where we are talking about the equilibrium constant. Right. So they say 4.5 times 10 to the minus 3 moles of nitrogen are added to, of each nitrogen and oxygen are added to an empty 0.2 container, which is sealed, right? They say write down the expression for the equilibrium constant for this reaction. Right, now, remember, the expression for the equilibrium constant will always be, it's going to be the product. In fact, let me write down the reaction first so that you can see it. Okay, so remember, reaction is N2 plus O2, giving us 2NO. Okay, so we have nitrogen, which is a gas, plus oxygen, gas, which would give us 2NO, which is a gas. Okay, now in this case, what we are simply saying, we want to write down the equilibrium constant expression. Please note, there's no need, and I see you guys like writing this product over reactants stuff. Okay, there's no need to write this down. Okay, all we need when we want the equilibrium expression, all we need is to write which one of the products. We've got NO as a product, so it means we're going to say the molar concentration of nitrogen monoxide. It is in gas form. Remember, for the expression, you only include gas and aqueous solution. So if it's liquid or solid, we do not include it in the expression. In fact, if it's liquid or solid, you can put a 1 in its in its stead, rather, right? So in this case, to say NO, now the coefficient here becomes the power. So this is going to be NO squared divided by N2, right? The reactants. Now, notice it's gas, so I'm including it. The coefficient is 1, so I'm going to leave that as power 1. And in this case, multiplied by O2, I'm including it because it's a gas. The coefficient is 1, so this would be to the power 1. So this is what our Kc expression looks like. Okay, right. Happy days?
Yes, sir.
All right. Now, in this case, they said to us, determine the concentration of nitrogen. Yes.
Can I please ask?
Yes, go
Yeah,
ahead.
I'm sorry. Yeah. So if on the side lapho kune nitrogen and oxygen, ne? So
Yeah.
if we replace it, ne, it becomes the
Yeah.
product side, then the part becomes the reactant. So will the product be N2 plus O2?
So you're saying if we were to write this reaction like this, and then which N2 plus O2, is this what you are asking?
Yes, sir.
Okay. Yeah.
Then
So if yes,
will it be the product side will be that on top, like with the
yes,
expression change?
yes, absolutely. So in this case, it means that now nitrogen and oxygen would be your products, ne? So as a result, then manje, your Kc expression would be N2 and O2, right? And its products divided by reactants. So in this case, it means that your reactant is now NO. So you'd say NO squared.
Oh, okay. Thank you, sir. Now I understand.
All right, sure. Okay, awesome stuff. Okay. Now let's go to the Kc calculation. Right. So they told us, remember, they told us, Uguti, we've got 4.5 times 10 minus 3 of each that were added to an empty container. Okay, they say determine the concentration of nitrogen monoxide gas that is present at equilibrium. Right. So what we're going to do is draw a table. Okay. We're going to say, so we've got three things there. And remember, we've got initial, which is in moles. We've got change, that's in moles. We've got equilibrium, that's in moles. And we've got equilibrium concentration, which is in moles per cubic decimeters. Okay, right. Now remember, what did we have? We have N2, we've got O2, and we've got 2 and O, right? Now they said to us, we started with, initially, we had 4.5 times 10 minus 3 of each, times 10 minus 3 of each oxygen as well as nitrogen, right? Now remember, the fact that they said to us they were placed in an empty container, what does that mean? It means at the time we had not formed nitrogen monoxide. So it means that the initial amount of nitrogen monoxide would actually be 0. I hope that makes sense to all of us, ladies and gents. Right, so in this case, then what do we know? We know that at equilibrium, did they give us anything else? Oh yes, they gave us the equilibrium constant, okay? They told us that the equilibrium constant that is present at equilibrium, okay, right, the equilibrium constant was that value, 1.1 times 10 to the negative 5. So Ruti sizokala with an example that is really this kind of daunting example, but you will understand it as I explain it nonetheless. Okay, right. So now they said to us we've got equilibrium, the equilibrium constant. But now here's the thing. We don't know anything else on the table. So remember, for us to draw the table, okay, we need to have some information so that we can plot any other thing, right? But here's what I'm going to do, okay? They wanted us to find out what is the concentration of nitrogen monoxide at equilibrium. Now, if you don't mind, I'm going to say, look, let's assume that the amount of nitrogen that I use in the reaction, remember when the reaction occurs, then I'm going to have nitrogen monoxide that I use, nitrogen. So if the amount is X, now this is where we're going to use our, I always say, I always draw this in a different color so that we remember. Please remember here, this is where you use the ratio, okay? So in this case, if I use an X amount, right, of nitrogen, look at this. The ratio says for every one of this, you will use one of that. So if I use an X amount, I will use what? An X amount because their ratios are the same. Now, the ratio for nitrogen to nitrogen monoxide is 1:2. So it means for every one that I use of this, I'll get 2 of that. So if I use an X amount, what will I use for this guy? It will be 2X. And please remember, ladies and gents, we only use the ratio only in this portion over here. Okay. Right. So now, does that make sense to everyone?
Yes, sir.
Yes,
Okay.
sir.
Now, I want you to think about it. I started with 4.5 times 10 minus 3. Remember, these are my reactants, so I'm using them, right? So in this case, I'm using an X amount. What would I have at equilibrium? It would be 4.5 times 10 minus 3 minus X. Okay, so that's what I would have. In this case, it would be obviously less X. Again, for oxygen, I started with 4.5 times 10 minus 3. I use an X amount. What do I have? It would be the same amount times 10 minus 3 minus X. And that is now for nitrogen monoxide. I started with nothing. Remember, it's a product, so you produce products, isn't it? I started with nothing. I produced 2x. What would I have at the end? I would have 2x. Okay, right. So now let's talk about equilibrium constant. So what do we, equilibrium concentration rather. We always say number of moles at equilibrium divided by the volume. I think the volume we're given as 0.2, right? There it is there, 0.2 cubic decimeters. So that means that my concentration is number of moles divided by my volume, 0.2. I'll do the same for this guy, 4.5 times 10 minus 3 minus x divided by 0.2. And then for this one, it will be 2x divided by 0.2. Okay, right. Now, you remember we knew the Kc value, né? They gave us the Kc value. They said it's 1.1 times 10 to the negative 5. So now let's use our equilibrium expression. We know that this is going to be NO squared divided by N2 times O2. So we're going to take all our amounts at equilibrium. And right now, all that's left for us to do is some mathematical gymnastics. So we know Kc is 1.1 times 10 to the power minus 5. Okay. NO squared, the value at equilibrium, this is the value. So this is going to be 2x over 0.2. Okay, but remember this is squared. Sorry. And I'm making a mistake here. Please remember, when you are substituting, you no longer use square brackets, you use round brackets. Né? Okay, because remember, square brackets in chemistry denote concentration. So now I'm substituting the concentration. So I need to use round brackets. Okay. Right, so this is divided by those two values, 4.5 times 10 minus 3 minus x, okay, all over 0.2. Now, all over 0.2. Do you agree that those values are exactly the same for nitrogen and oxygen? So if you don't mind, can I just put there a square? Do we all understand?
Yes, sir.
Right. So what I'm going to do, Mena, I don't want to be working with these difficult things. Let me take the square root on both sides. Okay. When I take the square root on both sides, I will now get rid of the squares. I will have 2x over 0.2, okay, divided by 4.5 times 10 minus 3 minus x over 0.2. Okay. And this would be equal to, let's see, square root of 1.1 exponent minus 5. Okay, so it's that difficult value there. 0.0033 da 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 da. Okay. Right. So 0.033 ton. Okay, I'm going to leave that value. Of course, you don't want to round off at this stage, right? Now, ladies and gents, please, I want you to be very careful on this one here, right? So, when you are working with fractions, do you know if I have 1 over 2 divided by 3 over 2, right? Do you see the denominators of my fractions are the same, né? Right? So once I have that scenario, then I can just drop down those denominators, and that will simply be 1 over 3. Okay, right. Now this is mathematics, ain't it? So in this case, I'm trying to simplify the maths for myself, so I can drop down the 0.2s. So what am I left with on the left-hand side? On the right-hand side, I have 2x over 4.5 times 10 to the power negative 3 minus x, okay, which is equal to, in fact, you know what, let's just leave it as square root of 1.1 times 10 minus 5. All right, are we all okay so far? Right, so if I want to write it as a fraction, right, so now let's cross multiply. So 2x times 1, that will give me 2x, okay, into, which is equal to, that will give me 2x into 1.1, square root of 1.1 times 10 to the negative 5, okay, into 4.5 times 10 to the power minus 3 minus x. I hope this is not exhausting, that you are still with me. Okay, so what I'm going to do is I'm going to divide both sides by square root of 1.1 times 10 to the negative 5. So what I do on the left, I do on the right. 1.1 times 10 to the power negative 5. That cancels that. On the right-hand side, I've got 4.5 exponent minus 3 minus x, okay? And on the left-hand side, now let's say 2, in fact, let's clear this, 2 divided by the square root of 1.1 exponent negative 5, okay? I get 2603.022, so we get 603.022x. Okay, right, everyone okay so far?
Yes, sir.
All right, so I'm going to take this x to the other side. Remember, it becomes positive. So I'm left now with, so it will be 603 plus 1. So that will be 604.022x, which will be equal to 4.5 times 10 to the power negative 3, right? And of course, what's left for us to do? We're going to divide by 604, that number there, 2, and we're going to divide 604.022, okay? That cancels with that, and we now want the x amount, okay? So we said we are taking that number plus 1. No, sorry. Let's delete that. Let's go outside. So that's plus 1. Okay. And then we've got our answer, and we are dividing by 4.5 exponent negative 3. Okay. And then we are taking the inverse of that. Sorry, delete. Okay. Right. So let's put it in you. Yeah, I get the number 7.45. This is times 10 to the power, see, 1, 2, 3, 4, 5, 6. Okay, to the power -6 moles. Okay, right. So I've gotten the x, the value of x, and sorry, Ruti, this is such a terrible example in terms of just the working out. But I'm trying to show you how to go about answering these kind of questions. Ne? So if you haven't done chemical equilibrium and have not mastered it before, please just make it a point, sorry, to go and visit it on our channel. Please let me know if you struggle, going there, because what we'll do is I can just send the link mhlambe later on. Okay. Yeah.
Will
So
do.
okay. Yeah. So that is what we get. However, remember what they asked us. They asked us to find the concentration of nitrogen monoxide at present at equilibrium, right? So this would be the expression for nitrogen monoxide at equilibrium. So we're going to take 2 times x divided by 0.2. We got the x. So the concentration of nitrogen monoxide would be 2 times that value, 7.45 times 10 minus 6 divided by 0.2. Okay, so let's do that quickly. It's that value multiplied by a month. What's happening? Okay, so I said that's so that's multiplied by 2. Okay, and divide by 0.2. Okay, so we get, okay, so we get 7.45 times 10 minus 5, and this is moles. Remember, we are talking concentration, so it must be in moles per cubic decimeters. Okay, ladies and gents, did it make sense now? Please let me know if there's any challenges.
Sam, I have a question. So,
Yes, go ahead.
so when you thinking you rounded off near the
Where?
6,603,022.
Oh, yes, but
Right?
remember in the calculation I didn't.
Or you did not? I also didn't
Yes.
round off, but I got 7,45 times 10 to the power of minus 8 to be my x.
Really? Minus 8?
Yeah.
Minus 8? I
Oh,
was.
oh,
No.
oh,
Yeah.
my mistake.
Please
Sorry.
just try and do it again. You should be able to get
Okay.
minus 6.
Thank you, sir.
Okay. All right, no problem. Okay. But besides that, in terms of the understanding, are we okay?
One last question.
Yes,
Yes,
go
I need to
ahead.
clarify this. So, can you please go to the table? The
The table, yes.
yeah. So, if I want to get the change of moles in moles, and I have the equilibrium. So I add the initial plus the equilibrium to get the change.
Say that again, you?
For example, I wanted to get I wanted to get equilibrium, and I have the initial and the change. Do I add those two to get the equilibrium?
No, you actually subtract.
Why? That's what I don't understand.
Okay, all right. Now, Do you mind if I take a different example? Ne?
Okay.
Let me do this.
Okay.
Let me do this. Let's just say let's take a reaction. Let's say we are taking which one should we take? Let's take. Okay, let's say this is the reaction. All right, let's just say for argument's sake, we've got 4.5 moles of sulfur dioxide, okay, placed, okay, let's say, right. Okay, 3 moles of oxygen, placed in a, let's say 2 cubic decimeter empty container. Right, now, what they can say, right, at equilibrium, we discover that, let's say, just for argument's sake, let's say 2.8, yeah, let's say 2.8 moles of SO3 are formed, okay, all right, or are present. Let's just say, man, hey, Mara, this thing, right, are present, okay, and let's say calculate the equilibrium constant. If you don't mind, I'm just going to say just calculate Kc. Ne? Right, I want us to do this one together so that it's got less hassles. So that I think all of us would be able to understand with an example that is less intense than the one that we did. Ne? Right, now, remember, what do? We're going to draw our table, right? All right, so we're going to say, okay, so there we are. We've got, what do we have? We've got SO2, we've got oxygen, and we've got SO3, but we need to balance that out. Okay, so that's 2 and 2 over there. Ne? Right, so we start with the initial, which is in moles. We've got change, that is in moles, and we've got equilibrium, moles, and we've got equilibrium concentration, which is in moles per cubic decimeters. Okay, please remember to write down the SI units, Zakona, so that we know what each one represents. Right, now look at this. We say, right, initially, what do we start with? We started with 4.5 moles. We started with 3 moles of that guy. So we're saying, okay, we've got 4.5 moles of oxygen, of sulfur dioxide, and we started with 3 moles. Now, we did say it was an empty container, or in this case, we were not given the initial concentration of the products, so we assume that it is 0, right? Now, I want you to please follow me in this. Ne? Now, in this case, then they will always kind of tell you what you have at equilibrium. Okay, so in this case, we found that we've got 2.8 moles of sulfur, sulfur trioxide. So we've got 2.8 moles of sulfur trioxide at equilibrium. Now, right, what are we going to do? We always start where we've got the most information, right? And where do we have the most information? On sulfur trioxide, right? In that there are 2 values there. Now remember, because it's a product, what does that mean? It means that the change that it underwent was that we produced it, right? Now, I want you to note, we started with nothing, and at the end, we've got 2.8. How much did we produce? We must have produced 2.8. Does that make sense?
Yes, sir.
All right. So when it comes to the products, and by the way, please, when you find time, also look at the example that I did. I think it's the last example that I did from the recent May-June exam on chemical equilibrium, and you'll see it's going to be an exception to this rule. But look at this. Because it's a product, you started with nothing, but you produced, so which means you added onto what you already had, which is nothing, and you've at the end you've got what? 2.8. Now, remember what I said. I said this part here on the change, this is where we use our ratio, right? Now notice this. For every 2 moles of sulfur dioxide, I form 2 moles of sulfur trioxide. What does that mean? It means whatever amount of sulfur trioxide I have, I will have the same amount of sulfur dioxide. So it means for 2.8, how much will I have? I will also have 2.8. Does that make sense?
Yes, sir.
All right. So look at this. For oxygen, for every 2 of those, there's 1 of this, right? So it means if I've got twice the amount, right, of sulfur trioxide, I'll have half the amount in this case, which is 1. So for 2.8, what's half of that? That's going to be 1.4. Does that make sense? Okay.
Yes.
And by the way, you can also do that using ratio and proportion. And it's as simple as this. You can say for every 2 SO2, you get 2 SO3, right? So remember, we didn't have sulfur dioxide. So for how many moles of sulfur dioxide will you get 2.8? And all you do is just cross multiply only the coefficients. So 2 times x will give me 2x, and 2 times 2.8 will give me 5.6. And if I divide that by 2, I end up with 2.8 anyhow. So in this case, that's where the 2.8 comes from, right? And then for this one, oxygen, we said for every 1 oxygen, we get 2 sulfur trioxide. So for how many moles of oxygen will I get? 2.8. And in this case, you cross multiply again, 2 times x, that was 2x. 1 times 2.8, that will be 2.8. And if I divide both sides by 2.8, I mean by 2 rather, x will give me 1.4. So that's where this 1.4 comes from. Okay. That's another way of doing it if you are not able to just easily predict. Okay, are we okay, ladies and gents?
Yes, sir.
Yes, sir.
All right. Now, then let's get to the part where we deal with equilibrium. And this is the part I wanted to explain and answer what you were asking. Now, because these are reactants, sulfur dioxide rather, I started with 4.5. And remember, with the reactants, I use reactants, right? So I start with 4.5. I use 2.8. How much would I have at equilibrium, right? So remember, then you say, well, it's 4.5. I use 2.8. In this case, we'll be left with 1.7. So it means I'll have 1.7 of sulfur dioxide at equilibrium. I started with 3. I use 1.4, right? And what will I have at equilibrium? Remember, it is a reactant as well. So how much will I have? It will be 1.6. Okay, does that make sense to everyone? So because it's the forward reaction that occurred, it means these guys obviously would decrease. it means this one will increase. But if it was the reverse reaction occurring, then these ones would increase and this one would decrease. Okay. Right. Please keep that in mind. Ne?
So say
Yebo.
I should always remember ukuthi makufika kuma reactants I subtract noma kanjani.
No, and that's why I'm saying it depends on which reaction is taking place. And you'll see from the example that I showed you. And that's why I've seen some textbooks putting minus here, minus and plus or whatever. I really don't like that, because what it simply makes you do is okay, every time it's a reactance, then I subtract. But that is not always true, because the moment you have the reverse reaction taking place, as I did say, there's an example that I did from the recent May-June exam, where there was the reverse reaction occurring, and now you found, Wuti, this one that is supposed to be the product is now the one that decreases, and the ones that are supposed to be the reactants are the ones that now increase. So in that particular example, you'll see that what you have at the end, you'd say 4.5 plus the 2.8, and that would be the amount that you have at equilibrium. So it would really depend on which reaction is taking place, the forward or the reverse. Okay.
Okay, sir.
Askisi for not answering you in certain terms, because honestly, I would be inculcating a misconception if I said to you yes, right? It's easy for me to just say to try and say yes to the question that you answered me, because that's what happens most of the time. But you see, angazi what you will get at your exam, and I don't want to tell you that yeah, it's always minus. It depends on whether the forward reaction is taking place or the reverse reaction is taking place. Happy days?
Yes, sir.
Okay. Awesome
Um,
stuff. Yes.
I also
Yes.
have a question.
Yes,
For
go
the
ahead.
table, does it matter? Like, does it affect the equilibrium constant we calculate if we use the ratios differently? Like, if we start using ratios at equilibrium, if we have like one of the moles, right?
That's a very
And
good
then
question.
work backwards. Does that change
That
anything?
that is a very good question.